brings us to the Holocene. Initially, people thought that the Holocene was bland. Nothing really happened. We come out of the Pleistocene, the craziness of the glacial, interglacial cyclicity, and we hit a flat spot, the Holocene, everything's good. But now that we start to look, we find that maybe things aren't so good. It's like checking the Carfax, whatever that thing is. You want to know the details. Just getting a good-looking car isn't good enough. Does the thing work? Same thing with climate. What's happening under the hood? We now know that a lot of things have happened under the hood in the last 10,000 years. Some of these things were good, some were bad, some were terrible. They sometimes affected isolated regions, and sometimes they were global. By 8,000 years before present, dense oak forests stretched from the Atlantic coast to western Russia. They also stretched from the Alps to southern Scandinavia. Europe's summers were several degrees warmer than today's, and the sea levels rose rapidly to near modern levels. During this hypsothermal, Europe was home to sparse populations of hunter-gatherers, many living along seashores, in river valleys, or by the freshwater lakes that were appearing as the ice retreated. Most of these Europeans were constantly on the move, following the seasons of plant foods, exploiting salmon runs, and pursuing migrating game. These people lived in small groups of perhaps a few families. At this time, heavy rains fell in Southwest Asia and North Africa. Oak forests grew along the flanks of the Euphrates and Jordan River valleys in what is now Syria and Jordan. Shallow lakes and semi-arid grasslands covered hundreds of square kilometers of the Sahara. These lakes are now salt beds. Over 5,000 years since the Scandinavian ice sheet began retreating, forests covered most of Europe, and sparse human populations had settled on the shores of the newly exposed Baltic Sea. At 8,200 years ago, 4 centuries of cold, much drier, near younger dry ice conditions brought drought to southeastern Europe and the eastern Mediterranean. Many farming settlements were abandoned as many communities retreated to the shores of permanent lakes and rivers, including the margins of the Black Sea, which at the time was a large freshwater lake. We can see the location of the modern Black Sea here. People would have gathered around these large freshwater lakes as a kind of refugia from the cool, dry climate that they were experiencing. And just for continuity, this is Abu Huraira down here. So farming again started here along this river valley in this fertile crescent that includes this valley and the coast of the Levant. The leading suspect of what was to happen, this catastrophe, is the Bosporus. This is also called the Dire Straits. And we can see from a picture taken a few years ago, I'm standing in Europe here. This is also Europe here. This is Asia here. This is what's known as the Golden Horn. I'm standing on the shore of the Sultanahmet in Istanbul, and this is the Bosphorus leading between Europe on your left and Asia on your right. This has been an important center for humanity for thousands of years, and this includes all major religions. We can see remnants of the Romans in this aqueduct and remnants of the Islamic past here in the Blue Mosque. So this water blasts through the Bosporus as sea levels rising, filling the Mediterranean Sea. It breaches this rim here and pours into the Black Sea basin in about a 3-week period. It's thought that you could hear this waterfall from a couple hundred kilometers away. Now what this did, the people that could run or move fast enough got out of the way, and they tended to run up or migrate up the Danube River Valley. So this gives them a conduit into continental Europe here. Many of these people left the Black Sea region, entered the forested European world. They propagated by using slash and burn technology. They cultivated rich weathered glacial soils. They cleared the temperate continent of its boreal forests. This type of slash and burn agriculture is a waste, as we saw in Panama earlier in the course. The first such farmers settled in the Danube Valley in about 7,300 years before present. This is a cartoon or artist rendition of a group of humans living along the Danube. This is a place called Lepenski Ver in Serbia, and it's one of the more important early slash and burn fishing combo settlements in Europe. Within 7 centuries, within 700 years, they had worked their way from the Balkans, from Serbia to the Netherlands, up to the northeast and east to the Ukraine. Now, only 8,000 years ago, these farmers were in Greece at the boundary of southeastern Europe. In about 3,000 years, most Europeans became farmers, and they transformed the landscape of the continent beyond recognition. It went from thick forest to mixed forest and agricultural land. At about 5,000 years ago, the world's first agriculturally based urban civilizations appear in Egypt and Mesopotamia. At about the same time, maize farming begins in Central America. Also about the same time, rice agriculture begins in Southeast Asia. So this brings us to the North Atlantic. When you do a climate change study, ideally you want to choose a site that is interesting. And it could be interesting because of a dramatic change that took place at that site. That's certainly the case here. It's also interesting if that site, the record you get from that site, can be applied to a much larger region. That's also the case here, as you'll see in this story. So this is a project we did about 10 years ago, or finished up 10 years ago, that we called Sea Ice and Sagas. Stable isotope evidence for 2 millennia of North Atlantic seasonality on the North Icelandic Shelf. Now, nobody lives on the North Icelandic Shelf, but clams do. And those clams record the water temperatures, and those water temperatures determine the air temperatures. So this is Kristen Dietrich. She was the graduate student of mine working on her master's degree on this project. She is pointing to the wrong location on the map, but that's okay. We're going to be talking about a series of giant piston cores obtained around the Vestfirðir region. This is a satellite image of Iceland. You can see why it's called Iceland, maybe. The Vatnajökull, which we've seen in other images, including the Blue Lagoon down here, is located right here. This is one of Iceland's ice caps. Other large volcanic structures on the island also have large glaciers associated with them. Why Iceland? Iceland is well suited for a climate change study because it's positioned between the Arctic and Atlantic climate regimes. Iceland is particularly sensitive to changes in atmospheric and oceanic circulation patterns, and Vestfirðir is one of the most sensitive locations of all. It's positioned near a major atmospheric pressure center, the Icelandic Low, and its climate is not obscured by continental climate processes. It is what it is, a North Atlantic climate. So who are the players here? This sort of brings the whole course together in a way. We have the East Greenland cold water current coming from the north, bifurcating north of Iceland to the east and to the west. We have the northward currents, the Erminger current and the North Atlantic current, also called the North Atlantic drift, and the Norwegian current. These are warm water currents. They bifurcate south of Iceland. The Erminger current bifurcates again to the west of Iceland. And it's this fight between the cold East Greenland current and the warm Erminger current that ultimately determines the climate of Iceland and the climate of Western Europe and Eastern North America. These are depictions of the maximum modern ice front and the minimum modern ice front. So in exceptionally cold years, like the late 1960s, this ice actually descended south of Iceland. And that cut off Iceland. It isolated Iceland. In most years, the ice front ends right about here. That's the midsummer ice front. And here we have the general position of the Icelandic Low, a major atmospheric center. And we're going to zoom in on this particular portion of the overall map. Talk about Vestfirðir, this digitate-looking thing sticking out of northwestern Iceland. What is the North Atlantic Oscillation? The North Atlantic Oscillation in the positive phase shows a stronger than usual subtropical high pressure center and a deeper than normal Icelandic low. The Azores high is extra high. Icelandic low is extra low. The increased pressure difference results in more and stronger winds crossing the Atlantic Ocean on a more northerly storm track. This results in warm and wet winters in Europe and cold and dry winters in northern Canada and Greenland. The eastern U.S. experiences mild and wet winter conditions for the most part. So the eastern seaboard, from the Maritimes down to the Bahamas, is mild and wetter than usual. In a negative NAO, the Icelandic low is not as low and the Azore high is not as high. The reduced pressure gradient results in fewer and weaker winter storms that cross on a more east-west or zonal pathway. These storms bring moist air into the Mediterranean, making the Mediterranean region wet, and cold air into northern Europe, meaning usually cold, snowy winters. The U.S. East Coast experiences more cold Arctic air outbreaks and therefore snowier conditions. In Greenland, however, West Greenland and northeasternmost Canada, we have mild winter temperatures. So we're going to take a look now at a couple giant piston cores located under these green dots. Talk a bit about local hydrography. This is important that you know when doing an isotope study what the isotope value of the water is. If it's a sample coming from the ocean, usually it's close to 0, but if there's significant freshwater influence, that can lower the isotope value considerably. So we have to beware of that. The fjords adjacent to these giant cores experience freshwater runoff from the coast, but this water remains in the upper 0 to 15 meters. And we went out in a boat and sampled the water for salinity and isotope value and confirmed this. Exchange with open shelf water occurs. This open shelf water is Ermiger Atlantic water for the most part, with a temperature about 5 degrees, salinity, which is normal, about 35 per mil, mixing with Greenland polar water, which has a temperature of less than 5 and a lower salinity. So we have to keep this in mind when doing our temperature calculations. The observed modern range of temperature in local waters is -1 in the winter to 11 in the summer, and the salinity ranges from 34 to 35.2 per mil. When you do a study like this, it's very time-consuming and very expensive. You want to focus on intervals where you think something might be happening. So we're going to focus on stratigraphic levels in the cores that correspond to notable warm and cold intervals. These intervals are based primarily on the carbonate content and foraminiferal isotope values of previous studies. So we recover mollusks, including gastropods, and also foraminifera, which are unrelated to these two, and we use them for AMS radiocarbon dating. This allows us to, if we have a full mollusk, both shells, take one shell and date it, use the other shell for measuring the temperature variability. So here we have a study from Isla Castañeda, a student of mine at Syracuse. She produced a record of the percent of carbonate going from about 400 years BCE to the modern. And you'll see lows and highs. These lows and highs correspond to something happening at those times. Those are going to be more interesting times to look at. When you throw in the oxygen isotope values of foraminifera, you see more bumps and wiggles, spikes and troughs. Again, those are areas of potential interest for us within the core. By radiocarbon dating portions of the core, in this case clamshells recovered from the core, we produce a series of dates. We assume a similar sediment deposition rate between dates, so we use a linear interpolation. And for the most part, it's pretty easy with this core. The sediment deposition hasn't changed for 2,000 years. Now, we find the shells by X-raying the core, so enough to destroy the whole core to get what we're looking for. If you know your clams, you can tell the species by looking at an X-ray. And we go back to our digital device here. We have 4 robots, one robot here, one robot here, another up here, and a 4th one underneath this stage. You can't quite see it. So this allows us to move this stage in 3 dimensions, up, back and forth, back and forth. And by using a micro drill bit, we can trace along growth features. So this is how it works. Here's a clam from off the coast of Iceland. This is a scale bar in millimeters. We are going to touch the surface of the clam with the drill bit. And this provides us with 3D coordinates, X, Y, Z coordinates. We're going to come back and touch another growth band with the drill bit again. This tells the robot where these points are in 3 dimensions. Now we're going to tell the robot to fit a curve to those points. And subsequently, we can tell the robot to take as many samples as we want in between those points. So just to clarify things a little bit more, we're not drilling holes into the clam. We're taking tiny slices. We're shaving material along one of these paths. Each path represents a day or a series of days in the past, and we're getting a temperature for those days. This is what it looks like up close. This is not Cassini landing on Saturn. This is a micro drill bit shaving a tiny slice of material off of a shell. This portion of the shell has been sampled already, so it looks nice and smooth and shiny compared to this natural surface here. So again, each of these tiny slices is going to generate powder. Each powder sample represents a couple days during the animal's life, whether it's yesterday or 2,000 years ago. So we use this temperature fractionation relationship that we saw before for otoliths. Clams are making their shells out of aragonite, just like fish make the otoliths out of aragonite. So we use the same temperature equation, gives us an accurate temperature. We tested this on a fingernail clam from New York State. This fingernail clam is about the size of your fingernail. And what we did was we microsampled it, generating these little data points, the little red spheres here. We compared them to the isotope value of carbonate that should be precipitated given these water samples that we took and given the air temperatures that were recorded just down the street at the meteorological station. So this was a clam that was growing in 1998 and 1999. And you can see that the clam pretty accurately records the bumps and wiggles in temperature. Now, we didn't do any massaging of the data to stretch and squish it to make it fit, but if we did, the fit would be better than what we see here. So this is a very simple Excel plot of 3 different data sets, essentially. So now we're going to apply it to the real world, the ancient real world, and look at a clam that lived about 2,400 years ago. So the isotope values are converted into temperature on the right y-axis with the isotope values on the left. So this is simply the number of samples taken from the point at which the clam started to grow. So the clam was born here and died here. So it lived through 4 glorious summers 2,400 years ago off the coast of Iceland. So we're going to, for the next portion of this lecture, talk about some graphs that are in this format. We have temperature here in these clunky looking squares, and carbon isotope values up here. We're not going to talk about carbon in this course, this portion of this course anyway. We'll just focus on oxygen and the temperatures that are calculated from that. So 2,400 years ago, the temperatures in the North Atlantic are about 7 degrees maximum in the summer. This is compared to 11 degrees maximum in the summer today. So the North Atlantic region is cold, but things are starting to heat up in Macedonia. This is when Alexander the Great was rampaging his armies across Southwest Asia and over to the Indus Valley between 330 and 323 BCE. At this time, there was more water than today, although much of this water was left over from an even wetter earlier period. So this vegetation, which is also relic like the water, allowed them to make boats, and these boats allowed them to cross the Indus River using trees that grow along the shore 2,400 years ago. Those trees are no longer growing there because it's much drier today. So Alexander took advantage of the higher precipitation and the relic water from the earlier, colder, wetter neoglacial period to conquer an area that today is, for the most part, dry, semi-arid to arid. 240 BC, temperatures are again around 6 degrees in the summer. 230 BC, we start to see a change. In fact, a pretty big change. We go from around 6 or 7 degrees in the summer up to around 11 and a half degrees in the summer, which is as warm as it is today. So at 230 BC, while it's starting to get warm in Iceland, climate is playing a very dramatic role in southern Europe. This is the time of the Punic War and the Second Punic War. Second Punic War is also known as the Hannibalic War. from 218 to 201 BC. And this was the invasion of Italy, the early Roman Empire, by Hannibal from North Africa. And he was very successful militarily, had some crazy ideas that are really cool. These would make great movies. In fact, they're used in some movies. But he ultimately failed in Zama, the Battle of Zama in Africa in 2002 BC, mostly as a result of not being supported at home politically. So the Roman Empire could have been the Carthaginian Empire if it wasn't for some weasels in politics in North Africa at the time. Hannibal is one of the more famous generals of the world, considered a military genius. He's the son of Hamilcar Barca, of the Barca family. In 221 BC, he succeeded his brother Hasdrubal, who was the commander in Spain at the time. We don't have any photos, obviously, of him. We don't have any paintings either. We do have a couple sculptures, so this is one of them. He's famous for this, rafting elephants across rivers, also marching elephants through the Alps. Two types of climate significance here. One, that there were lots of elephants in North Africa at the time. They're not there anymore. Two, that the elephants could be marched through the Alps, through passes that today are covered with snow. So as soon as the snow melted in those passes, Hannibal comes along and marches some elephants through to terrify the Romans. And that is only possible if the elephants exist and the passes are snow and ice free. This was, of course, used in Lord of the Rings for dramatic effect. The terror would be real, but the elephants weren't this big. So the Roman warm period, this period is now known as the Roman warm period, provided the warmth and moisture needed to supply the Carthaginians in their fight against Rome, and subsequently, ultimately, supporting the Roman armies in their conquest of the known world. By 130 BC, the warmth is off the charts. We're about 13 degrees in the summer. So we've gone from around 6 or 7 degrees in the summer to around 13 degrees, a couple degrees warmer than today. And as a result, the Roman Empire reaches its maximum extent. When climate is warmest, when farming is best, the Roman Empire is biggest. These farms in places like North Africa were enormous, and they provided food for the Roman armies to poke into surrounding territories. And like any big empire, you reach your zenith, your maximum extent, and then you roll back. It all collapses on you because these people living out here, the barbarians, the savages, are pecking away at you from all sides. Eventually, you can't support it anymore, and you become the former empire. Trade routes of the first century, from the Roman Empire to the Parthian Empire, Kushan Empire, and the Han Empire of China. Now, we talked a little bit about the Silk Route that went through here, the Genghis Khan Trail. This was a time when literally the whole known world was connected. As you saw, there wasn't much of a connection, but it was a connection. At 140 AD, our temperatures are decreasing. We're now below 9 degrees in the summer, down from around 13. That's pretty considerable. 4-degree drop is a lot. And these winters in particular are getting cold. At 410 AD, it's now back to pretty much the way it was in around 400 BC. And temperatures are down to the 6 to 7 degree range in the summer. The Roman Empire responds by collapsing. It splits into an Eastern Empire run by Constantinople and a Western Empire run by Rome. Constantinople became Byzantium, and Istanbul has had a bunch of different names. So this brings us to the origin of the modern world, the winepress of the wrath of God. This is when the Dark Ages came on and gerbils changed the world. It's why I'm speaking to you in English as opposed to Gaelic, for instance. And that's why Beagloin Brachagam and Sutmartuif don't work in this town. You don't know what that means, most likely. What it means, this is, I'll have a glass of beer and this means, hey, how's it going? So this is Irish, and this is Welsh. These were common languages at the beginning of the Dark Ages, and now they barely exist. On the whole, the British, who were the Celts, hated the Anglo-Saxons. They refused to have any contact with them. Even when they were out of their homeland, people were amazed that the Celts would have nothing to do with the Anglo-Saxons. They wouldn't eat with them. They wouldn't sleep near them. They wouldn't even say hi. They didn't even like the word. In fact, my sister and my brother-in-law, about 10 years ago, had 4 Irish high school kids staying with them, exchange students. And they heard that I did a lot of work in Ireland, so they wanted to talk to me. And so my sister hands them the phone, and I said, what do you guys want? And they said, Pog Mahone, and all started laughing. And I said, Tashe Sassenach. And they went, whoa, hey, oh. And they started laughing, and they handed the phone back to my sister. And she said, what did you tell them? They're going crazy. And I said, I told them they were Saxons. And she says, what does that mean? I said, well, it goes back a long way, but that's a major insult to an Irish person to call them a Saxon. To call them a super or a Saxon. And that'll get you punched in the nose. So they spoke of these impious Easterners, villains with dreadful claws. This was a monk describing them. Ferocious Saxons, name not to be spoken, hated by man and God. Most Britons, or the Celts again, would have liked to see them exterminated. This is a commemorative portrait on a hillside after a battle between the Anglo-Saxons and the Vikings, who came a little bit later. So how do we get here? Why are we speaking English? Well, the monk and historian Gildas wrote that pilgrims weren't able to visit shrines in the East, and they called this the unhappy partition of Britain, when Eastern Britain was Anglo-Saxon and Central and Western Britain were still Celtic. For the entire 6th century, until the 590s or so, not a single West British monk tried to visit, tried to preach, tried to talk to Anglo-Saxons in the East. So this brings us to a famous Anglo-Saxon, maybe. King Arthur. Was King Arthur real? Did King Arthur exist? Folklore and oral tradition suggest that at the time of his death, Britain plunged into a dark age. You see this at the beginning of the Holy Grail, which you can see depicted here. The historical record contained in tree rings suggests that the passing of this legendary 6th century king might have been a bigger disaster than was formerly realized. It's not just a fairy tale gone bad, it's a world gone bad. This is the legendary castle of King Arthur. This is in Tintagel in Cornwall, which is near Land's End in the UK today. Pretty impressive ruins. Problem is they were built about 700 years after King Arthur died. He probably didn't live there.